Nice. Lots of simulated applause and real applause from Harpreet. Harpreet, thank you for the amazing introduction. It's amazing how many ways we're connected. I didn't know that you were going to be introducing me today. Amazing to see you with Deep Learning Illustrated on your desk, making your way through it. I've seen you posting on LinkedIn as you make the progress. Very cool. So today's talk is on Tensorflow versus Pytorch, as Harpreet mentioned. So if you'd like to, you can get the slides from jonkrohn.com/talks. So there is a easy way to download them. You can head to today's date and then click on the slides button, and you'll be looking at the exact same document as I am. This is my puppy Obo, who it's possible will end up barking at some point in this room during this presentation. So look out for that. So as Harpreet mentioned, and as I've had up, I authored Deep Learning Illustrated a couple of years ago. And since I did that, there's one question that I get asked all the time. Probably about a third of the questions that I get asked are, so for my deep learning, should I be using TensorFlow or Pytorch? And so today's lecture is going to address that question. I'm going to start off by giving you a very quick high-level overview of deep learning, featuring some beautiful illustrations by Agley Bassens, whose illustrations are throughout the Deep Learning Illustrated book. So this is Yann Lequin, this is Yoshua Bengio, and Jeff Hinton. The three gentlemen pictured here, or illustrated here, were awarded the Turing Prize, which is the equivalent of the Nobel Prize for computer science. It's the highest award you can get in computer science. It's an academic computer scientist, and they were jointly awarded that honor in 2019 for their work on deep learning. It really has changed the world. Now, I could talk literally for hours about the history of deep learning, and I could do that with a whole bunch of illustrations, but we're going to skip to 2012 and to an innovation by Jeff Hinton and his colleagues at the University of Toronto, which was called AlexNet. So AlexNet is the single most important deep learning network that led to a lot of the architectures that we see today, and that caused the splash that allowed so many of us to be aware of what deep learning is, to see its impact. And so let me quickly run you through this model, which will also give you a great sense at a high level of how deep learning works if you aren't familiar with it already. So a deep learning architecture consists of several layers of processing. So this particular AlexNet architecture from 2012 has 1, 2, 3, 4, 5, 6, 7 layers of processing. In each of these layers, there are what we call artificial neurons. These artificial neurons loosely mimic the way the biological brain cells work. And this architecture, this deep learning architecture, loosely mimics the way that your brain processes visual information. So, just like your eyes get photons of light shone on them, and you could be looking at a cat, we can present a deep learning model like AlexNet with the pixels of an image. The first layer of artificial neurons in the machine vision architecture, in a deep learning machine vision architecture, is responsible for very simple processing. So there are 96 artificial neurons in the first layer, called a convolutional layer of this AlexNet architecture, and all 96 of those artificial neurons are pictured here. And so each little square is a different artificial neuron, and you can see what each one specializes in. And if you examine them, you can see that each one specializes in detecting a straight line at a different orientation. Some of them detect differences between black and white, others between green and red, but they only detect straight lines. And that's just like the first layer of brain cells in your brain that process information from your eyes. The second layer of artificial neurons can recombine information from the first layer. So you can see a sample of the artificial neurons from this layer here and what they process. And what you can probably make out is that these are combinations of lines. So curves and corners are represented by the artificial neurons in this layer. The third layer can recombine information from the second layer. So we have increasingly complex, increasingly abstract visual representations by the third layer, and then even more so by the fourth layer. The final layers of the architecture behave slightly differently. These are called fully connected layers. And exactly what that means is beyond the scope of what I could cover in this relatively short talk. But the idea remains the same, that these layers continue to recombine information from preceding layers, allowing the visual representations of this deep learning machine vision network to become increasingly complex, increasingly abstract as we move from left to right. By the final layer, our network can very accurately predict, assuming it has high quality training data, what image is being presented. So it could say, hey, I think there's a 99.9% chance this is a cat, and a 0.1% chance it's a dog, a 0% chance it's a horse or flower. So that's deep learning in a nutshell. And that particular AlexNet architecture that I just showed you, when it came onto the scene in 2012, it absolutely crushed all existing benchmarks for machine vision algorithms. So I've colored deep learning architectures in pink here, or rather my illustrator has colored them in pink, and non-deep learning machine learning architectures, which I'm going to call traditional machine learning architectures for the sake of simplicity. This could be regression models, support vector machines, what have you. And so those are colored in purple. And in 2012, Jeff Hinton and his team introduced their AlexNet architecture, which I showed you on the preceding slide, into the ImageNet Large-Scale Visual Recognition Competition, ILS-VRC, which is still the premier machine vision competition today. And you can see that the error rate was massively lower for this deep learning architecture relative to any of the other architectures submitted in 2012. So because of that, because of AlexNet having this incredible accuracy relative to what anyone in the world had ever seen before, everybody in the competition took notice, academics more generally took notice, and tons of people in industry took notice. So by 2013, just 1 year later, almost all of the entrants, and certainly all of the top entrants into this machine vision competition, were deep learning architectures. And in a few short years, deep learning theory based on this AlexNet architecture evolved suddenly and very effectively, evolved subtly, but very effectively to allow deep learning architectures by 2015 to exceed human accuracy in object detection tasks and image recognition tasks. And that has continued as the years go on. So deep learning has dramatically changed the world. Deep learning is all over the place today, and I'm going to show you some examples on the next slide. But at a high level, I wanted to fill in for you what allows deep learning to be so powerful relative to those other kinds of deep learning approaches. Now, this does depend on typically having relatively large amounts of data for training your models. It also depends on having relatively large amounts of compute available to you. But given those two constraints, deep learning architectures allow you to avoid feature engineering. So feature engineering, if you're not familiar with it, is a process in machine learning, which up until very recently was the most important part of building a machine learning model. And so what this involves is developing deep expertise in your particular data set, in your particular kind of problem. So if you wanted to build an algorithm for detecting human faces, you might spend your entire career studying how you can write functions to intake a photo of a face and scan over all the pixels with your function and pull out some kind of information that might lead a machine learning algorithm to be able to recognize that it's a face. downstream. So feature engineering is highly labor intensive, requires deep expertise. If you want to build a machine translation algorithm, you have to be a linguistics expert in the traditional machine learning paradigm. You have to be able to be an expert not only in the language that you want to translate out of, but also the language that you want to translate into. So again, many, many years of expertise required for high-level, high-performing traditional machine learning approaches. So as a traditional machine learning engineer, again, working with regression models, support vector machines, and other kinds of model approaches, you might spend 80 or 90% of your time engineering features and a small minority of your time actually training models. With deep learning, this is turned on its head. So with deep learning, you might spend a small amount of time engineering features out of your data, or you might not spend any time on it at all. You would typically spend all of your time training models, watching them train. They might take hours or days, maybe even weeks, depending on how much data you have and how much compute you have available to you. And so with deep learning, the expertise is not so much in your particular domain, but in how to design your model architectures for particular kinds of applications. So machine vision models, natural language processing models, and so on. But given those general modeling ideas, you can then apply what you've learned to build a state-of-the-art machine learning model without needing to be an expert in the particular domain or with the particular data. So because deep learning is so powerful, because it's typically more accurate than other kinds of approaches, it has now made its way in the years since 2012 into hundreds of use cases that impact you every day. So when your phone recognizes your face and unlocks, it's using a deep learning model. When your home device, like an Amazon device, like an Echo Dot or whatever is pictured here, I'm not super familiar with the Amazon devices, but when it recognizes your voice, that is using a deep learning algorithm. When you see deep fakes, so these people do not exist. These celebrities are fake. These were created by a kind of deep learning architecture called a generative adversarial network. Again, deep learning. And even complex sequential decision-making tasks like playing board games, video games, driving self-driving cars, any of these cutting-edge applications where machines have in the last few years overtaken human capabilities, guess what? Deep learning was involved. So if you weren't already excited about deep learning, hopefully you are now. And then it leads you to the question of, okay, I know that I want to be building deep learning models, maybe productionizing deep learning models. What library should I be using? So I just did this Google search this morning. So this is a completely up-to-date chart. I used Google Trends to find how frequently the 5 most popular deep learning libraries are searched for. So 2 of them right out of the gate we can eliminate as important. So Apache MXNet and Microsoft's Cognitive Toolkit, these can be ignored. They've never really been popular, and they're less popular than ever today. So probably not important. That leaves us with TensorFlow, Keras, and Pytorch. So TensorFlow a few years ago was clearly the most popular library. And part of what allowed TensorFlow to become so popular was the Keras library, which was originally created to make it easy to make deep learning models in a language called Theano. But the Keras project has now merged with the TensorFlow project, and Keras is now a module within TensorFlow. So when you learn TensorFlow today, in the last few years, Keras is actually embedded within TensorFlow, and it allows making deep learning models very easy in a way that it wasn't prior to Keras coming on the scene. So Keras and TensorFlow, these are intimately related. That leaves us with Pytorch left to discuss. So Pytorch, as you can see, is relatively recent. And it has overtaken, in some respects, TensorFlow. So depending on exactly what month you look at, Pytorch has overtaken TensorFlow, or at the very least, we can say that in the last couple of years, since the beginning of 2020, TensorFlow and Pytorch are neck and neck, kind of mirroring each other in terms of popularity. Just one other look, since a lot of people, when you want to be learning about deep learning, you don't just want to be learning about which libraries are most popular, but which ones are most likely to lead to a job. So in terms of number of postings, these data are now a little bit older, so we could expect that Pytorch is even more popular now. But you can see that in the US, where these data are from the website indeed.com, TensorFlow is more popular in job postings, but Pytorch isn't far off. So looking at the number of job postings that mention Pytorch divided by the number of job postings that mention TensorFlow, you can see that in some places like Seattle, even in April of 2020, there were almost as many job postings that mentioned Pytorch relative to TensorFlow. So it seems we're starting to get this idea that it might be a good idea to know both. Let's dig into that a little bit more. So what are the pros and cons of Pytorch? So you're going to see throughout the rest of this deck, I'm going to have a flame whenever we're looking at Pytorch code or a Pytorch topic, and water flowing whenever we're looking at TensorFlow code or talking about something related to TensorFlow. So we can think of Pytorch as being like NumPy. So if you're familiar with NumPy already, you will find it very easy to work with Pytorch. It was designed to behave very similarly to NumPy. The big difference between NumPy and Pytorch is that Pytorch is optimized for computing on graphic processing units, GPUs. So GPUs were originally designed to render graphics on your machine. So if you're playing a video game with lots of 3D rendering, the GPU on your machine will be getting used a lot. GPUs have typically thousands of relatively simple processors that can run in parallel. And as it happens, those simple processors are outstanding at the simple linear algebra operations that are at the core of all machine learning models, especially deep learning models. So Pytorch allows us to compute in deep learning very efficiently. TensorFlow allows us to compute very efficiently on GPUs as well, but it was ported to Python from C++. So it doesn't behave as Pythonically. If you're used to writing a lot of Python code, TensorFlow can feel a little bit weird because of how it was just ported over. Pytorch allows for a lot of flexibility. So it allows for something called dynamic auto-differentiation, or Autodiff for short. What this means is you can perform partial derivative calculus on any kind of object very easily, on any kind of equation very, very easily. And this dynamic part means that you can even change your model architecture or your deep learning architecture at any given point during training. So you could, for example, accommodate varying sizes of data. You could keep changing your model size to handle a big chunk of text, then a small chunk of text, then a medium-sized chunk of text, which is something that you can do in TensorFlow 2.0 and more recent versions of TensorFlow. But historically, TensorFlow had a static graph. And if you're going to use Keras to make building your TensorFlow models easy, then you will still be stuck with the static graph, which means that you'll need to futz around with your data in order to, for example, ensure that each data input that you have, each image that you have, each blob of text that you flow into your algorithm is going to need to be adjusted so that it appears to the model to always be the exact same size. So that is a big constraint with the modern Keras approach to building TensorFlow models. So just mentioned the Keras API. This is a way to make building TensorFlow models easy, particularly deep learning models. It's a really intuitive way about thinking about all of the layers of your deep learning architecture. So if you think back to that picture of AlexNet, where we had those 7 layers of artificial neurons, in Keras, you could have 7 lines of code representing each of those 7 layers. It's a piece of cake. Pytorch also has an API that makes building models easier. but I think it's actually overkill. It's a personal opinion. So you can already by default in Pytorch have layers that are almost as simple to build as with Keras. This fast AI API is designed to make it really, really fast to build neural networks, but I think it goes too far and you lose a level of control that I like to have around my model building. Because Pytorch was designed in Python, debugging when you have errors is easy. Typically, you can understand the error message that comes up, really straightforward. In TensorFlow, on the other hand, because of how it was ported over to Python, debugging can be really tricky. You'll typically get a really long stack trace, and then the error that you ultimately see at the end of that stack trace doesn't make any sense to me. And so I typically just copy it into I copy it into a Google search, and then a Stack Overflow article will come up, which will tell me how to fix the error. And I don't even really understand what I'm fixing. It just kind of happens. So debugging definitely harder in TensorFlow. As we saw in the last few slides, in production and in terms of jobs, TensorFlow is still more widely adopted today, although in academia, Pytorch is more popular for sure. In order to allow your models, whether they're Pytorch models or TensorFlow models, to execute efficiently in production, or even to train efficiently in production if you have a gigantic model or a lot of data or both, Pytorch has something called torch script just-in-time compilation that allows you to take your Pytorch model and compile it across all of the CPUs, GPUs, servers that you might have access to in a model training or production environment. Similarly, in TensorFlow, the TensorFlow serving library allows you to efficiently allocate your TensorFlow model across as many CPUs, GPUs, and servers as you have available to you. Some of the other cool libraries associated with TensorFlow that allow TensorFlow to be highly portable across lots of production environments include TensorFlow.js, so JavaScript library for deploying into your users' browsers and executing the model on their end in their browser as opposed to on your servers. TensorFlow Lite for having your model run on devices that don't have a lot of compute, like a phone, for example, or the computer in a car. The TensorFlow data and I/O libraries allow you to have your data preprocessing, your inputs and outputs to your model all happen within the TensorFlow, what's called a computational graph. And so that TensorFlow graph can then be ported across whatever devices you like. You create one TensorFlow model and you can move it from your servers for training. You can deploy it into someone's browser, onto their phone. So really cool to have all of these auxiliary libraries available to you. To summarize, Pytorch is more enjoyable for model design. TensorFlow is better for production deployments. Let's look at a couple examples of code to see why I say that Pytorch is more fun for building models. So for any of these code excerpts that I show you, there is a relevant place where you can grab that code and see it in context. So for example, if we are representing some data in Pytorch or TensorFlow, so whether these are model weights, data inputs, outputs from your model, we represent any of those data as something called a tensor, which just means a bunch of data. And so you might store your data in a vector, for example, a one-dimensional tensor of data. And as you can see in Pytorch, it's super easy to create a simple vector. And here's how you do it in TensorFlow. It's actually just as easy. You just get a lot of weird extra output information that you may not actually need. So it's just a bit less clean on the outputs. If you want to see lots of tensors and tensor operations in both Pytorch and TensorFlow, and also NumPy, you can check out my Intro to Linear Algebra notebook at my Machine Learning Foundation's GitHub repo. I mentioned Autodiff earlier. So this is a way of applying partial derivative calculus. So if you want to apply, almost any machine learning model, in order to train it, we need to differentiate an equation. We need to calculate the slopes of an equation. And so you can get out paper and pencil, and you can do that by hand, but the more complex your model gets, the crazier and crazier, more complex it's going to be to figure out how to come up with the derivative of a given function by hand. So typically, we want to rely on an automatic differentiation library like Pytorch or Tensorflow to do this differentiation for us and allow us to train our model with typically gradient descent. So automatic differentiation gives us the gradient, the slope that allows our model to learn, and then gradient descent adjusts our model parameters in order to actually have the model change based on training data and all of a sudden give us outputs that match the outputs we'd like to have. As a simple example, if you have an equation like y equals x squared, you may be familiar with the power rule, a derivative calculus rule, which means that if we want the derivative of this equation, we can call that derivative dy dx, and according to the power rule, x squared becomes 2x. So if our x value is 5, then we plug 5 in for x, and our derivative of this function, plugging x in, we get 10 out as a result. So in Pytorch and TensorFlow respectively here, I'm showing you the code that allows us to perform the same operation. So we define a function here or here, and we flow a particular x value into that function, say 5. And then with Pytorch here, we actually perform automatic differentiation, and we get back our result of 10, and same kind of thing here. In TensorFlow, we have to do things inside of this with statement, which is kind of clunky relative to Pytorch. So just another example of how things feel more Pythonic and easier in Pytorch relative to TensorFlow. If you want to see more examples of automatic differentiation in Pytorch and TensorFlow, you can check out my Calculus 1 notebook in my Machine Learning Foundations repo. In terms of actually designing a deep learning model, it's about the same in Pytorch and TensorFlow. So these are the same model architectures. It's pretty straightforward in either case. Each line here basically represents a layer of artificial neurons. And if you want to see more examples of this kind of deep learning model building, you can check out my DeepNet in Pytorch or DeepNet in TensorFlow notebooks in my Deep Learning with TensorFlow, Keras, and Pytorch GitHub repository. In terms of training models, with Keras, you can train a model in just a single line of code, but this means that, so TensorFlow Keras can be the easiest option for you for getting started on training models. But then I do recommend considering making a change towards Pytorch, which gives you more flexibility. So it takes more lines of code to represent this same operation that we're performing here in TensorFlow, but you have a lot more control in here, and you have that dynamism that I mentioned that allows you to have, say, different sized inputs coming into your model that you can't do in TensorFlow. Nice. So in summary, should you learn TensorFlow or Pytorch? Hopefully, I've made it clear from this presentation that you might as well learn both. In the job market, both occur all of the time. If you learn one, it's super easy to learn the other. As I just mentioned on the preceding slide, one of the easiest ways to get started with deep learning is by using the Keras module within TensorFlow to build your deep learning models. And then from there, you can learn how to do things in Pytorch. From that point, you'll probably get comfortable having fun and enjoying building your models in Pytorch, and then using the Onyx library, the Open Neural Network Exchange, to take that model that you built in Pytorch and port it over to TensorFlow, where you have lots of production options, productionization options available to you, like deploying in the person's browser, deploying on a phone, and so on. If you want to learn about more If you want to learn more about deep learning specifically, including following that pathway that I just described, starting with TensorFlow Keras and then making your way to Pytorch, check out my book, Deep Learning Illustrated. It covers everything, including all of the applications that I described: machine vision, natural language processing, creating fake images, and complex sequential decision-making with deep reinforcement learning. All of these core areas are covered in Deep Learning Illustrated. And as you could see in this deck, Egley Bassins did an amazing job of creating fun illustrations to make, learning hopefully as easy as possible. And I've heard from Harpreet, our host, that he's having a fun time getting his way through Deep Learning Illustrated. And it sounds like actually learning deep learning for the first time from this book. So if you want to get it yourself, there's lots of buying options at deeplearningillustrated.com. Lots of translations, Korean, Russian, German, and so on. And at least for the English language version in the US, there is a 35% off code on that site. Nice. So please do stay in touch with me. I have an email newsletter that is the most reliable way to get push notifications whenever I have new content coming out. So notifications about chapters from my next book, The Mathematical Foundations of Machine Learning. Whenever I've added new videos to my Mathematical Foundations for Machine Learning Udemy course, which is in partnership with Super Data Science, updates on Super Data Science podcast episodes, all of those happen in my newsletter, which I send about once a month, sometimes a little bit more than that if there's something really important to say, like the Data Science Go conference is coming up. But yeah, that's the most reliable way to stay in touch with any of the content that I create, almost all of which is free. I'd also love to be connected with you on LinkedIn. So feel free to connect, not just follow, but you can connect with me. If you were in the audience today, just mention to me that you were at the Data Science Go conference so that I know you're not a random recruiter or something. I have a YouTube channel where I push out lots of free videos on deep learning and the mathematical foundations of machine learning most recently. And if you're into Twitter, I do tweet as well. So yeah, please do stay in touch. Nice. Hope you enjoyed that talk, and hit me up with questions. I've got some in here already. So Chris has asked, why is this even a battle? So Harpreet, do you have any thoughts on that? Why is this even a battle?
It's like R versus Python all over again.
Exactly. It's exactly like that. That's a really good analogy because they're both great. They have such great use cases, and why not learn both?
Yeah, and I mean, your book is an amazing introduction to deep learning. Definitely, it is the first time I've, embarked on this deep learning journey, having, been in data science for a little bit of time, and I love the way it's written, and all the examples are in Keras. But I'm also finding myself going through another course simultaneously, the Stanford Natural Language Processing course, and that's all done in Pytorch. And I don't know, just learning both of them simultaneously has been a bit helpful. I guess at kind of a random question while people's questions pile in here, but at what point in someone's data science career would it make sense for them to embark on a deep learning type of journey? Like, for example, I've came through as a traditional statistician, working in biostatistics as you're familiar with, and working in more traditional machine learning type of roles. And now just recently, after a few years in data science proper, beginning to get into deep learning, how do you think that trajectory should happen for people?
It's a really great question, Harpreet. And it probably depends on how you're planning on applying your data science. Mm-hmm. So if you know that for whatever reason, based on your professional interests or the career that you already have, that you're going to want to be doing machine vision or complex natural language processing, then you can start off with learning deep learning. So by using a resource like Deep Learning Illustrated, or there's Udemy courses that Super Data Science has put out, Kirill Eremenko, so like Deep Learning A to Z, you can start with those courses, and you can pick up the critical machine learning content as you go. That said, if there's no urgency to be learning deep learning, then you can be kind of starting with the math. So you could do something like my mathematical foundations of machine learning curriculum. So like you, Harpreet, you already have this strong mathematical and statistical background. You understand probability distributions, and you kind of have this probabilistic model-based thinking. So you can develop that first in kind of an ideal world if you have an infinite amount of time. And then you can start learning the basics of machine learning. So great books like Hands-on Machine Learning by Aurélien Giron, or Super Data Science's Machine Learning A to Z course on Udemy. These allow you to learn machine learning from the ground up. So I guess the short answer is it doesn't really matter even if you don't have some pressing reason why you need to be applying deep learning right away. If you think, wow, deep learning is kind of the cutting edge, it's got a lot of the most headline grabbing applications today, has the highest accuracy in a lot of applications, I want to learn that first, you can absolutely do that. Go through Deep Learning Illustrated. It should make sense. And then you might think as you go through it, I'd love to really understand what's going on under the covers here. How does gradient descent really work? How are partial derivatives calculated? How are linear algebra operations allowing this deep learning model to work? And then you can get the mathematical foundations afterward, having learned how to do things at a high level. So long answer.
Yeah, no, definitely. That's very, very useful. And I know that people listening are, going to take a lot from that. Talking about AlexNet, it sounds kind of like deep learning is in its infancy-ish. Is that appropriate to say? What are your thoughts on that?
So there's a lot of different ways to look at that question. So neural network architectures, artificial neural networks, have been around since the 1950s. So a researcher at Cornell in the 50s named Frank Rosenblatt developed the artificial neuron that we see in architectures like AlexNet today. And then there's this continuous line of innovation from Rosenblatt in the 50s to a Japanese engineer named Fukushima in the 80s, a Frenchman who lives in New York named Yann LeCun in the 90s. And so there's this continuous tradition of neural network evolution. And since the 80s even, we've had those neurons layered deeply, meaning 3 or more layers of artificial neurons. So while the AlexNet architecture specifically has only been around since 2012, the deep learning ideas that enabled it have been around for decades. Mm-hmm. And the thing that allowed AlexNet to come to the fore in 2012 wasn't so much deep learning theory, although there were some small innovations that allowed training to happen more reliably as opposed to happening a little bit haphazardly in decades previously. But the two primary things that happened in the years leading up to 2012 is compute becoming relatively cheap and data storage becoming relatively cheap. So in order for these deep learning innovations that happened over decades to all of a sudden explode onto the scene, it required big data sets and lots of compute.
So talking about Pytorch being really big in academia, what downstream consequence will that have since it's being widely used in academia? Because you'll have students who are coming in through school just starting to learn it. Would you expect that this will eventually outrun TensorFlow at all?
It's possible. I don't think it's so much the academia piece that would require Pytorch to totally usurp TensorFlow. It's that we would need the massive army of open source contributors who have created all of these auxiliary packages that allow TensorFlow in production to be so portable and useful on so many different devices. So that's the piece that would need to be replaced. And maybe folks working from academia will start to do that more and more and more. So yeah, hopefully that answers the question.
Yeah.
For now, there's definitely a lot of room for both of them, just like there is for Python and R. And I see that we have one last question and 20 seconds, so I'm going to try to answer it really quick. Mm-hmm. There's a question that is deep learning making machine learning less attractive? No, because deep learning is just one machine learning approach. So deep learning is a specific subfield within machine learning. And so, no, it's not making machine learning less attractive. It's making it more attractive.
Absolutely. All right, guys, look, Chris wants us to smile so that he can screenshot this and get us on LinkedIn. So guys, do me a favor, take a screenshot. We're smiling and get us, tag me, tag Jon, DSGO virtual, hashtag that. Tell me what you loved most about this particular chat, and all the socials, tag us on all of them. Jon, thanks so much for stopping by. I appreciate you taking time to be here. And again, keep up the great work. I'm excited for the next book, man.
Thanks. Yeah, my pleasure to be here. Thank you for hosting, Harpreet.
Absolutely.